This is one of the most remarkable breakthroughs in energy storage, particularly for hydrogen. It's a hydrogen paste from Fraunhofer Institute in Germany. Researchers are currently working intensively to find new ways of storing hydrogen. Ammonia and boron nitride, among other substances, play a role here, enabling hydrogen to be bound with up to 90% greater energy efficiency. But this paste I'm talking about today is next level. We're gonna find out exactly what this solution looks like, how it works, and what is the potential of this technology. And with that, welcome to the German Science Guy. I'm Dr. Jakob Beautemps, and in Germany we say Los geht's. There's a lot of talk about hydrogen, and we have seen some improvement in producing it, like I showed in one of my last videos. However, one of the main problems with hydrogen is still its transport and storage. Hydrogen is either stored as a gas in tanks at very high pressure or in liquid form at around -250 degrees Celsius. Both are complex and expensive processes. Even in car tanks, hydrogen requires 700 times atmospheric pressure. This is why the tanks of hydrogen cars are super large and heavy, and the energy density advantages over lithium batteries are marginal, which is a problem in terms of mobility, for example. However, the use of hydrogen paste could change the transport and storage problem forever. The technology was developed by the Fraunhofer Institute and is considered a promising solution for hydrogen transport. To produce it, the first step is to hydrogenate magnesium powder. So magnesium powder reacts with hydrogen. To do this, both substances are placed in a special steered reactor at a pressure of 6 bar. It's like a large Thermomix under pressure. By the way, is Thermomix a thing outside of Germany? It is this cooking machine, and Germans go crazy about it. Well, this hydrogen Thermomix produces magnesium hybrid powder. The hydrogenated powder is grounded together with carbonic acid ester and metal salt in an agitator ball mill, which is a very fine mill. This produces a homogeneous mass with optimal conditions for the transport and release of hydrogen. The result after the reaction is collected in a separated container. It consists of magnesium hydroxide, water and ester components and can be recycled. The primary focus is on recycling the magnesium hydroxide, which is the largest component of the paste. It can either be processed and then used as a recyclable material in other industries or converted back into magnesium. This magnesium could then be used to produce new paste. It is therefore a cycle. The paste is manufactured using mechanochemistry. Mechanochemistry uses mechanical energy to trigger chemical reactions. Ball mills are used for this purpose, among other things. This is a rotating drum containing small stainless steel balls. Rotation and vibration generate mechanical energy, which then activates chemical reactions. The method is considered particularly sustainable and cost-effective as it does not use solvents, consumes little energy and emits low levels of CO2. Australia has also recently seen a mechanochemical breakthrough that came as quite a surprise, but more on this in a moment. To get the most out of the Powerpaste, it is stored in an airtight and moisture-proof container. This allows it to be stored for several months or even years. And Powerpaste has an enormous energy density of 1.9 kWh per liter. That is 10 times the capacity of lithium-ion batteries. This means that for the same mass, hydrogen paste stores 10 times more energy. To release the hydrogen from the paste, you simply have to combine it with water. This means that a truck using the paste would not need to visit a filling station, but simply change this bottle and add water. The really amazing thing is that half of the hydrogen produced is created by the added water, so even more energy without more storage capacity. 10 kilograms of Powerpaste yield 1 kilogram of hydrogen. That corresponds to an output of 1.6 kilowatt-hour per kilogram. So as you can see, I'm really excited about this technology because it is amazing. It will really change how we can use hydrogen. So what is going on there right now? A large Powerpaste production plant was supposed to go into operation already, and I've been following this closely, of course. And I also talked to the Fraunhofer Institute, the institute behind it. So the goal is 4 tons of Powerpaste should be produced per year in Braunschweig, a city in Germany, where the facility is located. There's a total of 6,400 kilowatt hours of energy. An average electric car could cycle the globe once with that. But, and this is more important today, Powerpaste is not only particularly suitable for various small vehicles, but also for households. If the production facility runs successfully, the Fraunhofer Institute wants to take the next step of working with external producers to manufacture Powerpaste on a large scale. Of course, there's one important point we have to talk about, and it is the price. But the final price of Powerpaste is still unclear. But what we already know is that the energy prices play a major role here. Until the production facility opens, however, work is also being done on other possible applications for Powerpaste. Together with the company Greenland, the Fraunhofer Institute has developed an emergency power generator for power outages. In it, a fuel cell generates energy from hydrogen. The hydrogen comes from the paste, which is stored in cartridges and fed into the cell from there. The reaction between the Powerpaste and water can be activated or deactivated simply by pressing a button. But in addition to the paste, there are other research approaches to storing hydrogen that I really want to mention. One international research project working on this is ShipFC. This is because ships emit enormous amounts of pollutants into the air. Global shipping emitted 833 million tons of CO2 in 2021. This is more CO2 than the entire road traffic in Europe emits. That is why researchers are working intensively on alternative emission-free fuels. ShipFC has set itself the goal of storing hydrogen in the form of ammonia. Ammonia consists mainly of two substances, nitrogen and hydrogen. But unlike pure hydrogen, which must be stored and transported at either minus 253 degrees Celsius or 700 bar, ammonia only requires a temperature of minus 33 degrees or a pressure of 9 bar at plus 20 degrees Celsius. Ammonia is therefore a great energy storage medium for the actual fuel. To obtain this, ammonia is first split into hydrogen and nitrogen on board and then fed into a fuel cell that generates electricity. The hydrogen is consumed, leaving pure water and nitrogen behind. A catalyst prevents toxic gases from being produced and prevents hydrogen and ammonia residues from entering the environment. This technology should also make long voyages with large ships reliably possible. And actually, there are already some results. There are already some ships using ammonia. But there are also other options that are exciting. A second option is to extract hydrogen from sodium borohydride powder. This is a focus of the H2 ships project in the NEO orbits. The 20-meter long ferry is currently being built in Amsterdam and is set to become the first ship to run on a solid hydrogen compound next year. For the drive system, the sodium borohydride is first mixed with high purity water and a stabilizer. The mixture is then passed through a catalyst, releasing the hydrogen. A fuel cell is then used again. Research is still ongoing to determine which stabilizer is the most suitable. One possibility would be caustic soda. Daimler Chrysler already operated a prototype car in the early 2000s using caustic soda as a stabilizer and sodium borohydride as a fuel. The stabilizer is consumed in the reaction, leaving behind sodium metaborate. This can be enriched with hydrogen again, and in this way the residual material is recycled into a new fuel after the reaction. But that's not all. There's another promising method of transporting hydrogen, and this has been discovered in Australia quite by accident. Researchers were actually looking for an alternative to petroleum distillation. Instead, they discovered the latest process for efficiently storing hydrogen. This involves placing boron nitride powder in a ball mill and feeding hydrogen gas into the mill. When the drum begins to rotate, the balls collide with the powder and the wall of the drum. This triggers a mechanochemical process whereby the powder absorbs the gas. This works particularly well because boron nitride has a small grain size and a relatively large surface area in relation to this. This makes a ball mill 90% more energy efficient than conventional separation processes. No aggressive chemicals are used in the process, and boron nitride itself is verified as a class 0 chemical. It is so safe that it can be stored at home. In general, the powder can be transported easily and safely. To release hydrogen, it only needs to be heated in a vacuum. And another advantage is that the powder can be reused multiple times. This means that no waste product is created. In addition, the process is not only possible with hydrogen, but with all gases, which is quite a breakthrough. But these new methods also have their disadvantages, like always if we talk about new innovation. And this brings us to the big hurdle of this video. It's a part in every of my videos where we look at the critical points of an innovation. We do this all the time, by the way. You also always in every of my videos find the sources linked here and then in the video description. So if you want to check anything, you can always do this. Okay, let's start with the big hurdle. So like I said, the Viking Energy is powered by the world's first ammonia-based fuel cell for ships. This is a major breakthrough. However, there's still room for improvement here. This is because a fuel cell does not convert all of the hydrogen into energy, and the splitting reactor upstream of the fuel cell is also unable to split all of the ammonia. Around 100 millionth of the ammonia used remains. This is only a small amount, but a full 12% of the hydrogen produced is not converted into electricity, which is of course a problem. Fuel cells that use pure hydrogen as fuel have an efficiency of around 60%, while those that use ammonia have an efficiency of 51.5 up to 57%. It is important to note that the production of hydrogen is not included in these figures, so the whole efficiency is way lower. But there's another hurdle. Sodium borohydride as a fuel, as used in the Neo-Orbis ferry prototype, is probably not the best solution there. Because apart from the question of how wise it is to use substances that mixes easily with water on a ship, there are other problems with sodium borohydride. For one thing, sodium borohydride is a toxic substance that must not come into contact with skin or organic tissue. However, in order to use it as a fuel, large quantities of it would have to be produced. Secondly, sodium borohydride has a market price of 15 euros per kilogram, which essentially rules out large-scale use from the outset. Perhaps this is why experiments with sodium borohydride have never progressed beyond the prototype stage. So you could ask yourself, what is the best method? Overall, it is difficult to determine the best method. However, hydrogen paste and boron nitride definitely have the advantage of not requiring toxic chemicals. Australian boron nitride powder is still in its infancy. However, first it must be determined how efficient the whole process is on an industrial scale. In addition, a tank must be developed to release the hydrogen in a controlled and mobile manner, and this will certainly take some time. And this leads for me to the conclusion that the Powerpaste, so the hydrogen Powerpaste, is maybe the ultimate way. If we compare these new methods with today's standard procedures in pressure tanks or the cooling of hydrogen, well, there a lot of energy is still used for storage and transport, and it is very complicated. This means less energy is available to use the hydrogen. With the new methods, storage and transport are low energy. However, more energy is needed to release the hydrogen and use it. So all methods therefore have their advantages and disadvantages. And the Fraunhofer Institute also believes that no single method will prevail. Instead, current and future methods in hydrogen technology will coexist. I'm still in contact with the Fraunhofer Institute and I still want to see what are the next steps, and I will try to get there because it is in Germany, I live in Germany, so I will try to make a video of this new plant that they are building. If you like to see this, please subscribe, and if you really want to support this, you could also be one of the members of the German Science Guy. With that way you support with a little amount of money this channel, and with that way I can, for example, pay somebody to film me going to this plant. So if you want to do this, you can always do it, but you don't have to do this. I will always keep making videos if you do it or not. And I just have to say, vielen Dank fürs Zuschauen, which means thank you for watching. See you next time, your Jacob.